We are going to start from basic introduction as well. So if anyone who has no idea or forget about how it works, so he can see what is multisim and what we can do here. So when you run the multisim, that is from National Instrument, so this is the environment that you get. You will have a toolbar for this file menu and so on. Then you have some direct uh, options that you can select from here. Then the third one is the important one for you that you will be using most of the time to place the components and to use them when they are needed. And most importantly, the one that you will be using along with this component section is this toolbar that is at the rightmost. If you take your cursor to any one of these, you will have multimeter, function generator, wattmeter, oscilloscope, 4-channel oscilloscope, and so on. And in the end, you have the lab view instruments as well. So you can use any of the lab view instruments that are available directly here. Most of the time, you will be using multimeter, function generator, and the oscilloscope. So let's begin with the our first circuit that is from pre-lab 1, and let's try to build this one. This is quite simple one. So if I talk about this circuit, can anyone tell me in this condition this diode is in forward bias condition or reverse bias condition?
Forward.
Forward.
Forward bias. Why? Because its positive terminal is connected to the positive of the DC source. If I want to make it reverse bias, so either I can reverse the polarity of the diode or reverse the polarity of the power source. So we will take this example and we will implement here. So we have three components: power supply, resistance, and what we call this
Ground.
diode. So here you can see we have this place source, place basic, place diode, place transistor, analog circuits, digital circuits, and so on. So let's go to the basic, as this is the source that we are going to use. So our source is not a power source, but it is uh, DC power. So when we pick AC power, it gives us symbol like this. If we pick DC power, so the symbol changes and it appears like this. So we'll just press OK and it will appear here. After that, what we need a resistance. So we will just press this button from the group and go to the basic. In the basic section, you will get the selection for the resistance, and inside the resistance you will have a lot of resistances that you can just pick from here and use directly into your circuits. For example, I pick 2.0 kilo ohms. This is the thing that we need. And after this, what we need a diode, and that diode is not here, as you can see. So we need to go to the diodes selection here, and here we have a lot of diodes that are available, right? So we will go for the standard diode, and the number usually that we use is 1N4001. So let's try to find it out. See, now you can see here 1N4001G, GP, RLG, all are same, just the difference between these three is that they have some manufacturing differences. So you can pick any one of them. I would suggest you to go for always GP. GP means general purpose, right? And just select it and it will appear here. That's it. And further, we don't know anything, so we don't want anything else, so we'll just close it. Now we want to make a connection. So this is again very simple. You just need to take your cursor to the end and it will turn like this, and just click on it and this wire automatically get connected to your cursor. Now you can take it anywhere you want and it will be connected. For example, you want to connect it to the resistance, so you bring it here, it is connected. Again, we want to make a connection between this resistance and this diode. This is done. And from this diode to this power source, right? This is all done. Now, if I want to see, uh,
Doctor, we need ground.
yes, you need ground. Just a minute. Yes. Now, if I run this circuit in this way, it will give me an error that there is no ground here and you need to place it. Right? No ground node was found in the circuit. To ensure accurate simulation, add a ground component and simulate again. So again, we will go to the same section and from here we will pick this, not ground, it is this one. Bring it here, close, connect this to the negative of the power supply, and now this circuit is complete. Now you can run it and it is running. But as we don't have any measurement device connected to it, that's why you cannot see any of the values. Now, which device should I use if I want to measure the voltage across the diode and the resistance?
Multimeter.
Multimeter.
Why not oscilloscope?
It's a DC.
Yes, this is DC.
Yes, the power source.
There is no need of, you'll just pick the multimeter and we will connect across the diode, double click on it, so this will appear here, and when I run the simulation it will give me a value. So it is around 0.6 volts, right? So now I can turn it off, right? And I can pick another multimeter that I'm going to connect across the resistance like this. Double click on it, so its window will appear here, and now run both of these and you can see the total voltage is 12 here. 11.4 dropped across R1, while only 0.6 volts approximately drop across R2. Oh, sorry, the diode, because this is in forward bias condition. Now, if I want to do a reverse bias connection, then what should I do? Do it simply the positive. Run it, and you will see that the whole voltage is drop across the diode. Now this diode has become
Open circuit.
reverse bias, and in the reverse bias condition the whole voltage get drop across the diode, right? So this is our first example. Alternatively, what you can do, you can keep it as it is, as it was, like this. Check it. You can just bring it here, and to make it reverse bias you need to connect this negative terminal. Now run again. See the same result, 11.99 voltages across the diode. Now in this case, if there is some load that is connected at the output, it will get the maximum output, that is 11 volts, right? While if this is connected in forward bias condition, then what will happen?
11 minus 12 minus 0.7.
12 minus 0.7, so this will be the output, right? Now I am going to ask you a very simple question. Which voltage at the output, for example, if the output is across this diode, is sufficient to run LED? 5.6 volts or 11 volts?
The output
Yes,
should be the 11.
it should be maximum, not 11, but maximum, whatever it can be, right? So let's do little modification in this circuit. See what will happen. What happened now? What is the output voltage at the moment? Here.
The output also 11 in the resistor.
Yes, because the output with the resistance. So it is 11.4 volts. So this circuit is more logical than the previous one. Just a minute, hold on. Okay, so this circuit is more logical as compared to the previous one. Why? Because when the diode will be forward bias, any load that is connected across R1, it will be driven. And when this diode will be reverse bias, the output will remain off. Now change this again to make it reverse bias. Okay, and now run. Now what will happen? The output will go very low so that it is hardly able to drive any load. So in this condition, this is a case where you can say if my diode is forward bias, then it will drive the load. If it is not forward bias, then it will not drive the load. Clear? Clear or not?
Yes, yes.
Yes, teacher.
Okay, good. So now let's move to our next circuit. Let us try to put an LED and see if it can show us a glowing result here. LED. See what is happening here? Because the diode is forward bias and this resistance is in parallel with this LED, so it is getting a 4.67 volts, and these arrows you can see they are glowing, right? Now I will stop it and simply I will pick another diode. And I will make it bias like this, and now I will see these arrows are not glown, that means the LED is off. Understand the concept?
Yes, teacher.
What do you add, Doctor, in the right?
This one,
This,
this is
yes,
this is LED that is
filter.
light emitting diode. When it is forward bias, it glows. When it is reverse bias, it not glows. It is similar to this diode, but this diode has no indication, right? But this diode has an indication. We will see in the lab physically. It is like a small bulb. It glows when it has sufficient voltage across its terminal, and it remain off if there is no sufficient voltage across its terminal, right? Forget about the details of this one. The concept that I want to demonstrate here was that if the diode is forward bias, the load is driving. It is not necessary that it is a LED. It can be a motor, it can be a fan, it can be a heater, it can be anything, right? And when this diode is reverse bias, so the load is off. Either it is a LED or anything else. So this was the main concept behind it. Clear?
Clear.
Now it's reverse, doctor, is it?
Yes.
Or forward?
At the moment it is reverse. If I play, you will see it is not glowing. Stop it and make it forward bias again to check the response. See, they are glowing. That means the LED is working.
Doctor, the voltage in D1, why it's 7?
Because now the circuit has become a
Because
a combination circuit, not just a series circuit in which we had only one diode and one resistance. Now, as you know, if we go back to this, you know what is this RD? Do you know what is RD for diode?
Diode internal resistance.
Yes. And how much it is usually? It is usually very small. As you can see here, it is written as 10 ohms just. Usually it is sometimes 50 ohms maximum, right? So when we connect one LED in parallel with this resistance, so what happened? It become a voltage divider. So the voltage that we were getting before connecting this LED, that was around 11 volts, it dropped to 4.6, and the voltage that we were getting at the diode of 0.7 volts has reached 7.5 volts. Why? Because when you have two resistances in parallel, one has a greater value and the other has a lesser value, right? So the maximum current flows through where we have the lesser value, right? So that's why this happened. If I remove this, again, you will have the same values.
Doctor,
Yes.
I have a question. Actually, I didn't know the difference, the main difference or the concept between RD and RR. So can you explain here the difference between RD and RR?
Like you don't know what is this RD and this is R. What is this R?
I know what does it refers to and what it affect on the diode, but
Okay.
The concept between the difference between RD and RR, it's not very clear.
This resistance is clear to you. What is this resistance? This is
Yes.
a physical resistance that we use in our circuit, right?
Right.
As a component. Now, this RD, this small one, you cannot see here anywhere, right? But this RD refers to the resistance offered by this diode during an operation. Because this is a semiconductor device, right? Composed of p-type and n-type material. When it comes under the influence of an electric field, the electrical charges accumulated, those electrical charges give some resistance in the flow of current. That resistance caused by the electrical charges is measured that, okay, it has a value that is quite small. For example, here it is taken as 10 ohms. Sometime it goes up to 50 ohms, but it has a value, right? That's why we don't have the ideal response of the diode that we supposed to have. But practically, there is some internal resistance that causes the change in flow of current because of this resistance. Clear?
Okay. What about the RR?
RR, I don't know what you are referring. Yes, RR is the reverse resistance of the diode, right? RR is the reverse resistance of the diode. When the diode become reverse bias, so what happen? It uh, inhibit or it stops the flow of the current, and that is usually infinity, right?
Mhm.
If
Okay.
the
Okay.
resistance is so big, that means it is going to drop all the voltage across it.
Yes, because my next question was the difference between RD and RR for its value. RD was 10 ohm and RR was 100 mega ohm.
Yes,
So okay, it's clear now.
one is forward resistance, that is very small, and the other one is the reverse resistance, right?
Mhm.
Here.
Yes.
Okay, now let's move to the second circuit that we have. This is what we were doing in the lab last time, and I asked you to do this and submit, but you were lucky enough that we didn't get the chance to complete it. So we will start from here one by one. Half wave, full wave, and then bridge, right? So stop it. Now, if you want to save your work, it is very simple. So this is what I have done. I will just go to the file menu, save as, for example, I save it as pre-lab 1. So replace it and that's it. It is done. Now, for example, I want to do the new one. So I will just press this new and it will ask me to whatever. Now this is my new design. I will save it as pre-lab 2, for example. So this is done. So this is pre-lab 1. This is pre-lab 2. So in the pre-lab 2, what we have a diode with a resistance, but with an AC source. So this is the only difference, right? So what we can do, we can copy Control C from everything and come to the pre-lab 2, and as we are dealing with the AC source, so there is no need of these multimeters, there is no need of this source. Now we will go to the sources, and from the sources we will select AC power. So this is the AC power. Close it. Right. And the good thing is that when you are dealing with the software in very less time, you can do a lot. And the modifications are very easy. You can play around very comfortably. So here the resistance value is 1 kilo ohms. So we'll just double click on it and change its value to 1 and click OK. Now it is 1 kilo ohms. And the AC source here written as 9 volts RMS and 60 hertz. Here it is 60 hertz but 120 volts. So we will change this as well. Now, obviously we need oscilloscope to see this. What we can do, we can check input and output both. Channel A connected at the input and this is channel B connected at the output. Double click on it and here you have the screen. Now run the simulation. It is very hard to see what is happening. So what we can do is that we can separate these peaks from each other with this Y position division, and we can increase volts per division to shrink this waveform so that we can make them apart, right? So similarly, if you want to see the clipping area, so just take it a little bit up and you can see it. Now if I close it, right, now this is my input, that is the complete sine wave coming here, and this is my output that is coming as half clipped. So this is half wave rectification of the signal. Now if I want to read the values, although they are appearing here, but if I want to read what is happening, so how I can read? Obviously it will be peak to peak voltage. What I am going to read, these are the RMS values you can pick from here, right? Why these are same, almost same? There is a difference of only 0.7. So input is 8 while the output is 7 because there is a drop of 0.7 across the diode. Now if you want to check the peak to peak voltage, then what you will do, you will see, for example, channel A, this is channel A, complete sine wave. So at the moment channel A is set at 10 volts per division and channel B is set at 5 volts per division. So let's talk about channel A first. So this is at channel A, and if we adjust it a little bit, here, so it is roughly 1 to 2.5 boxes in vertical direction multiplied by 10. So it is somewhere around 25 volts peak to peak.
Doctor,
Yes.
you can move the vertical column from peak to peak, and we can calculate the voltage. In top left, in top corner left, we can change the place of the vertical column, right?
Yes, yes, you can play with this.
Yes, and we can accurately actually.
Yes, you can do it like this, right? And yes, from a starting,
One of them and set to Y max value.
right? right? So you can do it like this by playing with these. I think there should be what we call it, horizontal as well, because usually these are not for the voltage, these are for the time period of the wave. All right, so the vertical ones should be here somewhere so that we can know. Anyways, if we just drag them out of the screen, so these are the default values that you will get here in terms
Doctor,
of RMS. If you are interested to get the peak to peak, then you can just simply see how big this peak from this point to this point, and then multiply it with this factor.
Doctor, here the input voltage is 8, but in the circuit it's 9 voltage. So why it's 8 here in the oscilloscope?
Yes, this is
In the circuit it's 9.
let us change this value to something higher, 20, and see what will happen. You cannot change any parameter while running, so you have to stop every time and then run it. See, because of very high voltage, even this diode is not able to cut the peak as it is expected to do, right? Instead of 9, let us try the 4 channel one and see, maybe there is some difference here. It is giving some attenuation at the output. Now here, instead of 15, it is giving. Okay, let's do one thing. Delete this and take the function generator. Bring it here. For example, it is 10 hertz and give it a voltage of 2 volts peak to peak. Where is VP? 2 volts peak. Connect this as an input. Ground and here. Now run it. Okay. When you are using the oscilloscope, either it is here or in the lab, these values that appear here in the either in the simulation or in the measurement that you perform in the lab, this tracing of the waves plays very important role. If this tracing is good and constant, then you will have more accurate values here. Otherwise, you have to do the manual measurements for it. This is the reason why this value is fluctuating so much. Now, if you just focus on channel A and play it, see, this value is fluctuating from 0 to 2 to -2, right? While it should not be like this. Okay. I will try to investigate it further how this can be fixed. But this thing is clear, how we can use multiple AC sources and what we can do to change the output with respect to the half wave rectification and full wave rectification. Now, if I remove this diode and place another one, but in opposite configuration, then what will happen? This wave shape is a little down, so we will bring it. This is the difference in between these two. If it is forward bias like it was before, so it was clipping the negative peak, but when it become forward bias, when it become reverse bias. So the positive peak start clipping. How you can verify which peak is clipping and which peak is appearing at the output? You need to overlap these two with each other like this. So you can see which peak is clipping and which one is not clipping. Now stop this and go back to your circuit and add one capacitor. We have two types of capacitor. One is this with straight line, see this symbol, and one we have this capacitor that is called electrolyte capacitor, and it has a symbol like this, one straight line and one curved line. What is the difference between these two? The basic difference in between these two is the polarity. This capacitor has no positive or negative, right? It can be used in either direction, but this capacitor has positive and negative. So we are going to use this one. Bring it, close it, or rotate it like this. The input is connected from the function generator and the output will be at the oscilloscope. Here will be connected run this. Here you can or you can keep the input up and the
Can you move the mini window to the right so I can see the connection, please?
like this. Okay.
Yes, yes. And you must, oscilloscope is now blocked.
Okay.
Yes, yes. Okay, thank you.
Doctor,
Yes.
do you have to change the AC power to generation function or
No.
it's okay?
Like I can delete this one and I can use the AC power again here connected to the diode, and this is connected to the ground. Double click, 9 volts, 60 hertz, and this input is connected here, and then you can run it. Obviously it is a big signal, so you need to change the voltage, right? And here but one thing we didn't see, this is how much. Did you notice the change in the output? Focus here. If this C, the value of capacitance is 1, for example, 1 microfarad, and I am running this, so the output is more or less same as we have the output before adding the C capacitor. Now I close this, I'm going to make it 10. And now I'm going to run. See, the output become steep, right? The negative, like the 0 volt is almost, the 0 volt level is almost vanish. Now, if I increase it further, maybe it will get better. This is the output, almost constant. Understand? So if we increase it further, maybe we will have just a straight line. See, almost DC. There is absolutely no change at in the output, right? So you can do this for multiple values of C. 1, 10, 100,000, and so on. Clear?
Doctor, what's the value of the voltage when it's a straight line, for example?
When it is straight line, yes, this is a very good question. For example, let us make it 1000. Okay, and then run it. Now, what I will do, I will make this original signal, that is our input, somewhere here, and I will just make 0 for this. Okay, and stop it. Now, what is the scale that I have for channel B? 5 volts. What is the position? 0. 0 means this line, this one, right? Why this one? You can see here. If I change this, so with respect to this 0, it changes, right? So I make it 0, 5 volts. It is 1 to 2.2, you can say, multiply by 5, around 12 volts. So this is around 12 volts appearing here.
Doctor, channel B, the upper one?
Yes, yes, channel B, the upper one. The straight line, right? How? See, this is channel B, where it is connected. It is connected across R. This is channel A, it is connected across the source.
So, Doctor, channel
Source is sine wave, this is sine wave. The output is DC level, this is the DC level, right?
Doctor, the peak of the sine wave, For channel A, what's the value for channel A?
For channel A, it is 1 to 2.5 multiplied by 10. How much?
Why it's not 9? Because the input.
Because this 9 is RMS, not peak to peak.
So we should multiply it by
1.414.
So it's 10.269.
10.269 for one peak. Make it double.
20.538.
20.538. This is peak to peak voltage. So this is peak, first peak, and this is the second peak. If you want to measure half, it is easy. Take it as, sorry. Again, make it 0. This is 0. So forget about either the negative peak or the positive peak. Just measure this one. So how much it is? Here it is cutting here.
Will be 10.269.
1.2 multiplied by 10. How much it will be?
12.
Will be 12.
12. So roughly it is fine.
But when they multiply 9 by 1.148, it will give us 10.269.
As I told you, there are some errors because of the tracing. You need to set them as good as possible.
Okay.
So this point is clear how you can get the value of the DC level and how you can get a value of one peak and how you can get the value of two peaks altogether.
Yes, doctor.
Clear? Okay, good. So now what we have. So this is we did. Now let's implement this one, full wave rectifier. You can select any component and just press Control C, and to paste it again just press Control B. We don't need this, but we need a diode here, and only one resistance is needed, and it is connected here, it is connected here. This is the ground here, and yes, this will be grounded as well. Just to make it clear. Clear? This is how it will work for the full wave rectifier.
Channel B, doctor, in the resistor for the output or what?
Channel B is the output, yes.
In the resistor, huh?
Yes, in the resistor.
Okay.
Let me take it here. Okay. Now it is okay.
Yes. Why it's not 18, doctor, the input?
Because every diode is acting separately with one source only.
So when I want to measure the input, where do I have to put the channel A?
And this is where I have connected. See here with this diode only. I didn't connect anything here.
Oh, okay. Okay.
Okay, then what else you have to do? You have to put one capacitor similar to the previous one. Basics capacitor. Okay, bring it here. Again, if you notice that there is with less value, there is a very little, like almost a negligible change in the output. But if I stop it, double click, increase the value, now run it, see, it is significant. Now again, if I make it 100, okay. Okay, it's almost DC. Perfect DC line at the output. So this is how it, but usually what we do, we don't do it like this, that okay, why take 10, directly take 1000. No, we do it stepwise, like smaller value, bigger value, then see which one is good for you, then pick that one and use in your circuit. Because capacitor, resistance, or inductor, they all are passive components. So they consume power. So if they consume power, then like it is a loss for the output. So you need to optimize first that which value is good for you, and then you can pick the appropriate one. Clear? Any confusion?
Doctor,
Yes.
how can I measure the peak voltage and the peak tweak? I didn't understand.
Okay. So for example, we have this sine wave in channel A.
Okay.
We will make it 0. Sorry. like this. It is at 0 position. 0 position means 50% of the signal is above this
Above, yeah.
and 50% is below. Now, for example, if you want to measure only peak voltage means either you will take the positive peak or the negative peak, right?
Right.
First, let's try to figure it out. How much is the positive peak? This is completing one box and around 1.2 boxes, right?
Yeah.
This 1.2, we will multiply it with this 10. So how much it will be? It will be 12 volts, peak to peak. 12 volts peak,
Peak.
right?
Okay.
If you want to make it peak to peak, just multiply it by 2 because this is a sine wave. Whatever is in the positive cycle, it will be in the negative cycle as well. So it will become peak to peak.
Yeah. Okay. Thank you.
Okay.
Okay. Thank you.
Okay, guys, any confusion? Anything that is not clear? Hopefully it is easy. Now after this,
Doctor,
you have to do this one as well. Full wave bridge rectifier. So this is how you are going to make it. So this will be your next circuit. Then you have pre-lab 2 is done. Pre-lab 3. This is biasing circuits. You need to use two sources. One is the function generator and the other one is the DC source as well. And then you need to see the effect of these. What will be the third one? And then have you done the transistors or not?
Not yet.
Done?
No, we haven't.
Not yet? Okay. So you have to complete till pre-lab 3. Then transistor we will do next time. Okay.
Just pre-lab 3 or 1 and 2 and 3.
1, 2, and 3. All of them.
Okay.
Okay. 1 and 2 we already did. From 2, just full wave rectifier is left. So you have to do it by yourself. And then pre-lab 3 for the DC biasing circuits. All right. Any confusion?